This is a talk which we usually perform with my friend Błażej Kubiak, but today I'm alone. But nevertheless, the plan for this talk is to first get extremely excited. And I am dedicating 7 minutes, especially for that, because the world of technologies to which we are all contributing with our code simply deserves that. Within the next 22 minutes, we will truly understand the concept of convolutional neural network by a quick coding Python session. And for the rest of the talk, I will go through our own, a bit more challenging real-life project where you will hopefully see amazing possibilities of modern AI. So amazing that you might even get scared, for which I especially dedicate the remaining minute of my presentation. Okay, let's talk about science fiction, a classic from 1982. In this scene, Harrison Ford is analyzing a photo using a hyper-mega computer. It is year 2019, so it can obviously zoom and enhance without any physical reason. But this is not the end. This computer can even look around the corners. Wonderful technology. This film is a classic. It's great to watch, but although the film was shot when I was still very young, even then, I could feel something was not right. And I'm sure everyone here who watched this film felt this strange embarrassment in this scene. If you did, well, we still haven't reached 2019, and the world of science already says we are actually able to reconstruct details that seemingly could not have been captured by a camera due to its physical limitations. But okay, we can believe in zoom and enhance, but looking around the corners, come on. The end of 2017, guys from MIT and Google published a method in which using a camera, you can actually trace objects around the corner. It is based by looking at indirect reflections, as you can see, and you can trace these objects with centimeter level accuracy. Isn't it amazing? Maybe we cannot still see the face of the android lady around the corner, but it is not 2019 yet. Now, this technology was developed by people from blood and bones, just like us. The next scene, Eagle Eye, film from 2008, where a super intelligent computer is trying to take control over the world. People try to hide from it in a soundproof room, switch off everything and hide in shade, but the machine reads their conversation from the vibrations of water. Impossible? 2016, guys from Microsoft, Adobe, and MIT published a technology which does even better than that. In a second, you will watch a video of a flower listening to music. It's a video. Now it's the same video again, but the music is reconstructed from the micro vibrations of pixels caused by sound wave hitting the flower in this video. Amazing? This technology was developed by people from blood and bones, just like us. Finally, awaited by everyone in this room, David Hasselhoff and his talking car. It talks, well, that's not too extraordinary. It knows what it is talking about, and it can describe its environment better than Eliza Orzeszkowa Niemen. Fiction? 2015, a machine is able to semantically segment an image and generate grammatically correct sentence describing it. All these images descriptions were generated by a machine. Is it impressive? Well, if this is impressive, you are not ready for the next slide. Also, 2015, generative adversarial networks learn to draw photorealistic images based on what you say to it. So no one has ever made this photo. This bird does not even exist. Similarly to any of these. This is how a machine learned to imagine a sentence. And this technology was developed by people from blood and bones, just like us. But let's not forget that our car can actually drive itself. Impossible? Come on, you should already know for some time how much is going on in this field. For example, in TomTom, since 2015, self-driving car technologies are being developed extensively to enable cars hit roads globally. And these technologies were developed by people from blood and bones, but not just like us. I could tell you exactly who wrote these patents, but ladies and gentlemen, I'm very shy. Okay, so the cars drive by themselves, robots do their job on their own, drones learn to fly, machines learn to see. So we are living in amazing times where all of these technologies are at our hand and we can participate in their development. So I am sure that you are now getting thrills to start this amazing adventure by classifying cats and dogs. I'm not going to do this for you, but we will start with something easy to get some fundamentals like classifying faces into glass carriers and normal people. Do we need AI for this? Well, maybe, but let's first try to think about some traditional step-by-step solution. So we have a sample lady. To detect her glasses, first let's find some edges in this photo. To do that, we apply horizontal and vertical edge filters to the image, and speaking mathematically, edge filters will be just small matrices which correlate well with changes in color intensity. And then, by filtering, we mean, in fact, convolution or correlation, which is simply sliding such a filter across the image, multiplying the pixels, and adding everything. Is there anything in the world easier than that? No, there isn't. But however trivial and however obvious, convolution is the most important operation of today's talk. And that's the result. Now let's zoom out to look at our image at a further perspective, but we will not do it by typical resizing, because with typical interpolation, we would lose all the edges which we have just detected. They will be blurred. So instead, not to lose the edges while resizing, we will keep the maximum value in our pixels while resizing, instead of interpolating and averaging. This is called max pooling, and is there anything in the world easier than that? No, there isn't. But however obvious and however easy, max pooling is the most important operation of today's talk. Now at this scale, we can come to detecting our frames, which will be just a rectangle shape composed of vertical and horizontal edges. We convolve, we zoom out, we detect the glasses as two frames, so just two dots. And then finally, looking at further perspective, we can easily classify this result. If the middle pixels are much brighter than everything else, we probably detected glasses, which is here for 97%, which is good. Now in code, an image is a matrix and many multi-channel images is a tensor. So here n, because we have n images, by 200 and 180, by 3 because we have RGB color image. And if we design a filter, it also needs to be free channel because we have a free channel image. So after filtering, the result would be just n one-channel images. One channel because, as I said, convolution sums up everything, even across the channels. But we could design more filters. So one for top edges, one for bottom edges, left edges, so like 4, and then for every filter, the result would fall into another channel. Details are not important here. What is important here is fact that we're in fact designing a graph of TensorFlow. And there actually is a library with that name designed by a company doing quite well on the market at the moment. You know what I'm talking about. So there's no reason not to use it. So we will use TensorFlow today, and we will first create an empty graph, and then use some session to feed the data placeholders with our images from the disk. And in fact, for performance, even loading the data can be part of our graph. Now I see this question in your eyes. Where is this artificial intelligence? Nowhere. But please don't sleep and beware, because if you are planning to sleep now, I'm telling you, it will arrive suddenly. Now, because I have only one hand for coding session, other for the microphone, we will code very slowly. So let's start our implementation. We need TensorFlow, NumPy, OpenCV, and OS. We build our graph. We read the data, we run the graph, and we show the results. And in our graph, we put placeholders for input data. This will be 200 by 180 pixels, one channel. We don't know how many, hence the none. We also create a placeholder for the labels. Because we will load faces with and without glasses from different folder, so we know who is who, and labels will be 1 for glasses and 0 for no glasses. We will soon prepare a class, let's call it filters, which will have separate method to create and return a filter that we will need. One for edges, as you can see, one for frames, one for glasses, and one for final classification. Now the graph. The graph is very simple. First, we take our data from placeholder, we filter it and zoom it out, as we discussed. First, we detect edges, and we zoom out by 10 times. Then frames, and zoom out a little bit more. Then glasses, zoom out a little bit more, and finally, we classify. In the end, we will have some result. Let's calculate some metrics, how well we did on more examples versus the labels. We can do it automatically because we have loaded the label for every image. So we can just compare our detection with the label. Easy. So let's calculate accuracy and cost. Accuracy is simply the percentage of correct predictions, where prediction can be just right or wrong. Cost is something more. It is defined as a continuous function. For example, detecting glasses for 97% for this lady seems correct. But a well-justified question is, where did the 3% go? And the 3% is a loss. In another example, for some reason, our detector was really confused. And while it was still correct, the loss was here much greater than for the lady. And finally, when our detector sees Harry Potter, it is 99% sure he has glasses. But however sympathetic we could be for this decision, the loss is huge and unforgivable. So we have our metrics like this. We need to load the data. So let's create class for that. We have photos in 2 folders. 0 are people with healthy, typical eyes, and 1 is the elite with the glasses. So let's create a method which will load the data. We will work on several photos at once in batches, but as we mentioned before, we will perform the actual loading of images and labels as part of our graph. So we need to create a session for that, which we will do now. And finally, we will want to display some results of running our session on our load data, which we put in place of the placeholders. And with the same data, first we will print the metrics, which we have just done, and then we will display some visual results, like images showing what's going on. Okay, so now we would need an hour or two to implement all that stuff. But most of these things here, the ones in red, which we are not yet implemented, are really trivial. So I don't want to spend time doing that. So I will try to use my another hand to make it a little bit quicker. But if you're trying to follow, well, my aim is not that you understand every line being typed now. I'm showing the full coding session to give you an impression that, in fact, you can do all this experiment within the reach of 1 or 2 hours of coding. And during this talk, we will focus on the most important part only. So we have all the helper functions and placeholders for the methods defined. Let's focus on the problem. So we need to implement filter and zoom out. We will filter using convolution, which we have in TensorFlow. We will filter and shift our mask one by one and path the results to have the same size as input. And now let's implement the mysterious filter. In fact, 4 filters, 3 by 3. What is a filter? I already told you. It's just a matrix that will correlate well with the features that we are going to detect. So the left edge would be just decreasing the intensity from left to right, for example, from 2 to 1 to 0, and so is our filter. The right filter is just the flip of the left, and the top and bottom edge filters will be just the transpose and the flipped transpose of the left filter. Very easy. We have the 4 filters. Let's run and see the results. And perfect. We have 2 example faces, one with glasses and one normal. And we have our 4 filters as we define them. And then finally we have our results. Okay, I'm talking too loud, yeah? Okay, now good. So every filtering result is stored in a different channel. Now, if you look carefully at this, you will find something disturbing, in fact. The first 2 channels and the last 2 channels are very, very similar. In fact, they are symmetric. That was quite obvious because the left filter is just a negative of the right filter. So, in fact, in our left channel, we will see the detection of right edges in the negative part. Yes, and in the right channel, we will see the detection of the left, which is not something which we would like, because we would like every filter to have a single responsibility, and now it's wrong. But we can easily fix that. We can just get rid of the negative part, cut it off. It's so easy. But before we do it, please try to think how you would call a function which cuts off the negative part. Maybe cut off negative, maybe negative to 0, but respect to the guy who came up with a super intuitive name, rectifying linear unit. In short, ReLU. But that's not the end. The world of science went crazy. ReLU is believed to be the greatest breakthrough in the world of artificial intelligence. You can see it penetrating into the world of pop culture and art. It's 0 and X. Is there anything in the world easier than that? No, there isn't. But however trivial and however obvious, ReLU is the most important operation of our today's talk. So we have it implemented in TensorFlow. Let's add it and show the results. Okay, we now have our edges detected without the negative part. Beautiful. Now let's zoom out using max pooling, we will zoom out by zoom times with a zoom stride and traditional padding, and then show the results. If you remember, after detecting edges, we set the zoom out to 10 times. And now when we run it, we see it's quite aggressive, and you can see the so-called pixelosa effect. Maybe that was a bit extreme, but now in the original image frame of a single ocular was like 50 by 50 pixels, yes? And now, after this pulling, every ocular is just like 5 by 5 pixels, and we can easily create a small and effective filter for that. So it's very nice. Let's do it. It is a filter working on 4 channels, because we have a 4-channel image now, and because in the 2 channels we detected left and right vertical edge, and in the last 2 top and bottom horizontal edges, we can create our typical frame detector as a rectangle and closed by vertical edges from left and right and horizontal from top and bottom. Very easy. Let's run the result, and we can see 2 beautiful frames detected as pair of bright pixels in the last image, and they are separated also by 2 pixels. And for the non-glasses lady, nothing detected, which is nice. So our glass filter is a no-brainer. We need to detect 2 dots. Okay, let's get dirty with our implementation. Okay, we are detecting glasses. 1 here, 1 here, done. Okay, we run. And in the result, we see a beautiful shining dot somewhere in between the eyes of the lady with glasses. And that's very good information, and nothing for the other lady. So now, after a few lines of really trivial classification code, just multiplying some matrices, we arrive at a final result. We finish with just 2 pixels per image corresponding to 2 classes. Top lady has glasses, so the first pixel corresponding to glasses shines more white. By the way, I am not calling it a second pixel because I respect myself as a programmer and I count from 0. So the lady at the bottom has no glasses, so the 0 pixel shines more, which is a great result. Okay, adding a few more guys and running our program. Well, really good. First glasses found, second found. Now, the third and the fourth, we are actually reached by the brutal truth about life, which says that not all glasses look like windows. So as you can see, for more difficult cases, like a different perspective and so on, our filters didn't work. What to do? Let's sum up our status. We designed a network composed of layers of just 3 operations, very easy. Convolution, ReLU, max pool, and for each convolution, we manually crafted our filters. You can see all of them now. We actually designed every pixel in each of these filters by hand, and our solution worked well for happy cases, but in general, for more difficult cases, it didn't. So could we make it better? Probably we could. We would need just to play with these filters, tweak and tune them to detect more difficult cases, look at more results, tune again, and upon adjusting these filters, see more and more examples really working well. Okay? So we could do that, but we will not. Instead, we will set our filters with random values. And then, by looking at more and more examples with labels, we will let the machine optimize them for us. And we will do it by adding just 1 line of code. So, ladies and gentlemen, it is arriving. They tried to capture this moment in the Terminator. They tried in the Matrix. but it is actually you, ladies and gentlemen, staring at this line of code being typed in. It is you witnessing the death of handcrafted human solution and the birth of artificial intelligence. Yes, minimization of the cost function. Artificial intelligence is basically just minimization of the cost function. Good old maths put into powerful computers. But is it disappointing? If you expected supernatural phenomena and the touch of the magic wand, the truth might hurt you. But on the other hand, if you realize what we can achieve with such theoretical simplicity, it just blows your mind. In our case, while writing this code, even our operating system got intimidated by the fact of emerging artificial intelligence, and it also asked for an update. Coincidence? I don't think so. But anyway, after a few technicalities, your convolutional neural network is starting from some random values, and step by step, seeing more examples, will be able to learn the optimal filters to do your job. By seeing more and more labeled data, it will shape itself. And similarly to us, as you can see, it will first shape some primitive edge filters at the beginning, maybe a bit skewed, but you see them for sure, followed by some more and more sophisticated features. And here we will arrive by 80% of accuracy, which is maybe not a great result, but it's a very small network. And now, we don't need to craft our filters by our own, because the network will do it for us. So we can make it bigger. And then we can observe how the machine crystallizes solution beyond any handcrafted design, reaching accuracy here of 100% on the validation set. So, is deep learning just about stacking more layers as the complexity of the problem rises? Not exactly, because every layer comes with responsibility and risk. Deep networks are really hard to train because they are trained by backpropagation. And so the gradient propagated to the first layer can become unstable. It can vanish, and the layers will learn extremely slowly or will not learn at all, or it can explode. And as this field of science evolves, new ways to solve this problem arise, from smart initialization of weights, regularization, gradient clipping, and design of new activation functions, up to solutions that are so clever that you get thrills when you read a scientific paper. Like introducing interlayer auxiliary networks to speed up the training by Google, or residual connections by Microsoft to put every detection in the context of previous layer. We could talk hours about various solutions emerging every day. Probably at the moment, someone is writing a paper that will revolutionize the way we think and the state of the art. But what seems to never change is the fact that to properly train anything, we need loads of data, sometimes hundreds, sometimes thousands, sometimes millions. So is this respected by the newest science fiction from 2008? The Expanse, distant future, a group of main characters is looking for a missing girl, searching through old video logs, having only one single photo of a girl. Will the algorithm be able to find a girl having a single training example? Of course it will. Impossible? 2018, December the 1st, Warsaw, GDG DevFest conference, a project by Krzysztof Kudryński and Błażej Kubiak will reveal how to make that happen with a few mathematical tricks. So, let's talk about it. We want to train a network to find the girl in the video log. We could try to train it to classify the girl versus someone else, but we have only one positive sample of the girl versus millions of negative samples of other faces, so it is a bit unbalanced. What is balanced? Chuck Norris is balanced. Why? Because if we train it for Chuck, then we have in the internet more photos of Chuck Norris than all other faces of other people altogether. So if that was the case, we would turn this task into a simple classification problem. We would need to train it with millions of Chuck's faces and a million of other faces, and we'll be able to easily classify into Chuck or not Chuck. Are we happy? No. Because if we want to find a different person, we would need to train it again. Instead, what we want, in fact, is having a pair of faces, a reference face, and a sample face. We want to classify them into the same or not the same, although sometimes you can clearly see the similarity. If we succeed with a network defined in such a way, we could provide a reference which is not Chuck Norris. And if trained properly, we would still get a proper answer. But how to train such a network? In fact, there is a class of specialized networks solving that problem. Such network does not output a class, as you can see. It outputs a vector. In other words, it just... Hello? Okay, sometimes the mic is fading, but... So it just detects, outputs a point, a vector, so a point in a multidimensional space. And we want to train it in such a way that such points for two different faces are far away, and for the same persons are very close. So here, in fact, instead of a standard loss function as we used before, we define a so-called triplet loss function, and training here is quite complicated. Okay, and there are papers about it, so you can try to read them if you want. But today we will try to achieve similar results, but with our own very simple network, which we will train here in 5 minutes. What we will do, we already agreed that training a network for classification of faces into celebrities like Chuck, Seagal, or other legendary heroes is easy. So we will download such a network from the internet and we will cut it in half, removing the classification layers. Now the last layer will be some vector. So we can just run this network for two faces, but because it was not trained like before using a triplet loss, we will just subtract the two vectors and train our own very simple network to try to tell us if this difference says the faces are the same or different. How we will train it? With celebrities. Again, we will download a dataset called Labeled Faces in the Wild, containing labeled celebrities, thousands of them. And during training, we will select doubles of random faces from the training dataset, run the first network on both faces, and then training our small network with 1 if they are the same, and 0 if they are different. And we will do this time in Keras because it's so simple and nice. If you are starting to play with machine learning, go for Keras. It is actually a wrapper over TensorFlow, CNTK, and some other stuff, but the API is like a dream of Uncle Bob. As I said, we will just add 3 fully connected dense layers, set up an optimizer, compile the model with binary cross-entropy loss function, and feed the model to our data. So let's now run it. Excuse me for a second, I will just, okay, how to do it easily. Wait a second. Oh, you can see it, perfect. So we are just running it. And what we really like about Keras is that you don't need to write all these printing functions. It does it for you. So you can just look. By the way, it's learning very bad. So I will stop it. Sometimes it just decreases the. It learns bad because it's the random seed puts you in some strange place. But now it's learning much better. The validation set is still like 92%, 84, which is a bit jumpy, but at least we are in some nice region. So we will finally, okay, at the end on the validation set, we have 82%. That's not a lot, but the network is small, and maybe it will not work always, but it will work. And let's see how, because I have something prepared here. Okay, I will need to check. Sorry. Okay, it's working. So I need a volunteer. Can anyone be a volunteer for me? And come here, whoever. Now, this computer is without the GPU. We usually take Błażej's computer, which is much faster. So I hope it will. Come on, see you. It does not see you. Maybe you can come here.
Be seen.
Because the light at the back is killing me. And look at the camera. Okay, perfect. I have you. Now you can sit down and okay. First try. It's me. So it's red. Oh, it's her. I'm so sorry. It never happened. No. Okay. What's going on? It's really large, really sorry for that. Okay, but all this, I hope our drone will find you and will be able to. Come on. It's very blurry. Come on.
Yeah, we got.
I don't know why. So it should work better, but this stuff. Okay, so it didn't work too well, but as you saw, this was only 83%. We could train it a little bit more into the time. We could make a network a bit better, and probably we would succeed even more. But you can see the possibilities are quite nice. You saw we detected our missing girl with a totally different face expression. Here she was like this, in the other was like not very happy. We are making photos of her. So you can imagine the possibilities. And if you can't imagine, then is it going to work? Come on. Okay. Slides. Sorry. Oh, okay. Okay. Oh, okay. Don't panic, live demos always work. Okay, does anyone know what that is? If not, the top cross is what the person is looking at, and the cross below is what the machine generated by analyzing their brain activity. And more examples here. To me, it is a bit disturbing. Maybe it's not a fully deserved reading in your mind yet, but that's clearly a first step, already tested and documented in the literature. Soon, the machine will be able to read your mind, and it is going to learn any task you give to it, and it will always do so by optimizing its loss function. So whether you are designing the network to save the planet or to win the board game, please make sure to double check two things. First, to set the cost of human life to infinity, and then check if infinity is properly implemented in an environment. Thank you very much.